Hello, everyone. Welcome to Smarter Industrial Fault Diagnosis with Knowledge Graphs and Large Language Models. Today we have Wan who will be presenting to us. I'm going to hand it over to Wan to take it away.
All right. Thank you so much. Good afternoon, good morning, everyone, wherever you are now. So yeah, my name is Wan Razaq. You can just call me Wan. So today I'm going to present about my projects, which I've done during my master thesis. So this research project is part of my master thesis in the Business Information Technology program, University of Twente in the Netherlands. And the title is about smarter industrial fault diagnosis with knowledge graphs and large language model. So basically the application of those two technologies, KG or knowledge graph and LLMs for manufacturing companies, specifically for fault diagnosis of machines. And then this project has been done together with a manufacturing company in the Netherlands called Mintrus, that I'm going to talk in details later, and also a research institute called Fraunhofer Innovation Platform for advanced manufacturing. So a little bit about myself. So I'm from Indonesia, but now I'm actually living in Germany. I'm just studying my research work in Germany in University of Münster. But in the past 2 years, I studied masters in University of Twente in the Netherlands. But before that, I spent a couple of years in the industry as a product manager and also business development in several technology companies in Indonesia. Before I start deep dive and in explaining my projects, I wanted to show you the prototypes, the final versions of the prototypes. So imagine you are working in a manufacturing company and you have a problem with your machine, and then you could ask a chatbot or assistants, "Hi, I have a problem with my machine. Can you help me?" So the system or chatbot would just happily answers you 24/7 with very accurate answers. Of course, I can help. Could you provide more details about the problems you're experiencing with your IBM machines? For instance, specific symptoms or error messages could you help down the issues. So this we are going to talk about how I came up with this prototype. Okay, regarding the agenda, we start with the problem statements. What's the problem that facing by workers in the shop floor or from a manufacturing company, and then some theoretical backgrounds, and then methodology, and then case study, and then each artifacts that I've developed, the knowledge graph and also GraphRAG chatbots, user evaluation, and also conclusions. So we start with the problem. So why is diagnosing machine faults are so hard? So as we can see, as we know that in a manufacturing company, manufacturing really relies on machines in doing their operations. Just a second of downtime with the machine that could create a really negative impact for the manufacturing company, because they could lose productivity, they could lose operationality, and also it would affect the profitability of the company. But then doing troubleshooting for a machine is also hard, because in general, no clear instruction for troubleshooting, because the information of the knowledge is saved within the head of the experts, of the engineers. So no clear instruction for troubleshooting, especially when it comes to machines that are really complex in terms of component. The second problem is expert knowledge is written down but highly scattered. So this is the problem that we can see in many manufacturing companies, especially companies that are, I would say, small to medium-sized companies, because the knowledge about the faults are saved, let's say, in an Excel file, and then it is scattered for years. So they don't have such system like maintenance system for saving and managing that. So the knowledge is highly scattered. You could also imagine, if when it is highly scattered, how what would happen if these experts are leaving the companies or resigning or even retired? So the knowledge would be lost, and also it would affect the continuity of the operationality of the company. So this is really a problem, and it really requires an urgent solutions for manufacturing companies. And then a little bit about theoretical background. As you might know, I'm sure that you guys here are really aware and expert in this regard. So these two technologies, knowledge graphs and also large language models, are really in a trend, I would say, right now. And we know knowledge graph is here for quite some years already. But with the rise of large language models, we could see the interrelation between these two. So knowledge graph is a structured network of facts and relationships, and large language models is AI that understand and generate human language. So these two have um, interrelation between each other. So knowledge graph, uh, uh, and so LLM, when it's augmented with the knowledge graph reduces hallucination in LLM. But on the other hand, LLMs is also can be coupled to the knowledge graph in regards to the tasks for related to the knowledge graph. So for example, LLM can help knowledge graph in constructing entities and also relationships. So if we combine these two technologies together, it could make sense of maintenance data and also help engineers to diagnose faults for machines. So that's the idea. And then, what were the research questions that I'm going to discover by this research, and how how can LLMs and knowledge graph improve of fault diagnosis in manufacturing? So this is the general research questions. So specifically, I want to search for the accuracy of knowledge extractions when it's coupled with an LLMs. And then what would be the impacts of maintenance data quality? Because maintenance data, especially when it is highly scattered, the quality is also low. And what would be the impact for the quality? And also the performance of the final prototype, which is a chatbot, in real fault diagnosis. So that would be the research questions. All right. So, and then comes the methodology. So I started with data collection and preparations. And then from that, I built the knowledge graph with the help of LLMs. So, and then the developed knowledge graph would be used for final prototype, which is a GraphRAG based chatbot for fault diagnosis. So this is the sequence of methodology that I use during this research projects. Okay, so as a case study, so this research has been done together with the Mintras BV. So this is one of a medium-sized manufacturing company located in the Netherlands, in a city called Kerk, in the south of the Netherlands. So the company mainly in the industry of ceramic and diamond processing. So they serve customers in semiconductor industries, in telco company, and so on and so forth. So as you can see in the bottom left of the slides, there is the examples of the products that they are producing. So it's a small components used in electronics devices, in telecommunication devices. So products such as head spreader, sub-mount, optical packages, and so on and so forth. So basically, electronic components such as in a fiber optics, I would say, in the telecommunication industries. And then specifically for the machine, so this research is tested of or has been done in an IBM machines. So IBM stands for ion beam machines. So basically, this machine is used for etching and depositions of thin layers. So this is really a micro scale materials machine used for etching and depositions of materials, for producing the products that in the bottom left of the screen, as you can see. And this machine is highly complex and hard to troubleshoot because it consists of many subsystems. So there are subsystems for the neutralizer of the ion, and then there's also a subsystem for holding the materials. There's also subsystem for cooling, subsystem for vacuum, and so on and so forth. So this is complex, and there why the approach of using knowledge graph and also LLMs in line with this, because the machine is complex, so we need to model the complexity of the machine using a knowledge graph. So there, why this approach is really good. Okay, first, so the knowledge graph. Okay, so how I came up with the knowledge graph. First, I started with defining the ontology, which is how we model the faults. So there are 4 nodes or 4 levels for the entity. First, it's called the fault location. So there, where the fault is occurring, and then from the fault location, it connects with fault symptoms, which is the symptoms of that particular fault, and then from that fault symptoms, there are labels for fault reason, which is why such faults is occurring, and also the measures, which is the solutions. And then these labels are connected with some entities such as has faults caused by and also mitigated by. So this is the ontology or the schema that we are being used for developing the knowledge graph. And then what are the data? So the data consists of 2 sources of data. First is maintenance logs. Because this is a company based in the Netherlands, maintenance logs are written in Dutch, and then it is written freely for the past 15 years in Microsoft Excel, so you can imagine how complex it is. And then manual books of that particular machine from the OEM. This machine is manufactured by a company in the UK, so the manual books is written in English. And then from so those are the source of the data. And then I start to do annotation. So this annotation is used for. So I entered 25 cases, 5 for few shots, and the other 20 is for evaluations. So this is an example of the annotation. So as you can see, this is written in Dutch. So you can see that this is the case ID. It is the storing of fault cases. And what are the issues? The issues is sustained for list HE drugs. So the system lost pressure of the helium, and then compressor Urstan, and then that's the location of the fault, which is the compressor, which is the part of that machine. And then the drug out, the pressure out is 192 psi, and then the drug out is 50 psi. That's also the symptoms. And then another symptom is maat slepend geluid. So that means the compressor makes dragging sounds. Maybe there's a friction problem. So yeah. So this is the annotation that I did, and then I did this for 25 cases. Okay. Okay. Then I evaluated with the 20 cases. What were the results? The results was pretty good. So I used 4 benchmarks, which is exact matches. So 51.5% exact matches. So what the LLM is extracted and what are the annotations. And then mismatches, this is some entities are, this is not completely matches, but maybe slightly different in wordings. but still accurate. So in total, it's around 69% or almost 70% accurate. And then missing is what we annotate doesn't appear in the LLM, and the potential hallucination is 20. But when it comes to the potential hallucinations, so after I dig dive, so it turns out that actually the LLMs was even better in extracting the knowledge than the human annotations. So yeah, so this is really good. So this is the example of the schema. So I forget to explain. So I extract the entities by using OpenAI GPT-4 together with the framework called BAML, with the hope that the final extraction really structured, really clear, and also follow ontology that we've defined before. Okay, 15 minutes. Okay, so what were the schema or the BAML schema and prompting that I'm using for entity extraction? So as you can see, this is the examples. So I use few-shot prompting, meaning that for such prompts, I put some examples of the fault cases and also what would be the output format, and also what would be the examples of that particular language. So as you can see, so this is the prompt. You are an expert in analyzing technical maintenance logs. Extract the following entities: fault locations, fault symptoms, fault reason, fault measures. And then here are examples of extracting structured data. So I give examples from 5 cases that I annotated before. Is written in Dutch, and this also the target entities from the examples. And then you can also see I use BAML schema. So with this, so this is really good because we treat the prompts really as a function. So it really follows a structure that we defined, or the ontology that we defined, the data types, the format, and so on and so forth. So the final extraction is really clear with this. And yeah, as you can see, this is a function: extract fault info, log text strings, the fault report. So we really treat the prompting as a function with this BAML schema. Okay. Now, so after I evaluated with those 20 cases, so I extract all extract entities from all data sets, not only from the maintenance logs, but also from the manual books, which is in PDF. But with that, I use multimodal LLMs, OpenAI GPT-4o, because this PDF I extract first. I change first to an image and then use the multimodal LLM GPT-4 because that's easier. Because that's each PDF has different structures, so it's kind of hard for directly extracting with the text formats. And then with that, I get a structured output in JSON format. Okay, now after the JSON out, after the extraction in the JSON format, so there comes the knowledge fusions. So all the entities are programmatically fused to Neo4j, and then I did the entity resolutions, meaning that some entities that are actually the same or maybe only different in terms of language, I resolute this. And I use manual entity resolutions using algorithm Levenstein similarity and also APEC procedures. So as you can see, entities such as rotati tafel and rotati tafel, just difference in space, there's actually the same entities, and then I merge that. And then also entities such as compressor and with a capital and compressor without a capital, I also merge that. And accelerator cards and accelerator cards and accelerator boards. That's the left is in Dutch and the right is in English, but it's actually the same. So I also merge that. So from that, so initially there are 739 to 715 entities. 759. Now it's merged to 715, and it's really enhanced semantic vision and connectedness, because now all the symptoms and all the location are now really connected, and we really can see the connection that we didn't see before. So that's how the knowledge graph really beneficial in this case. Okay, so this is the extracted knowledge graph. Yeah, as you can see, this is the whole cluster. Okay, I zoom in. Okay, these are the examples of a location neutralizer. This neutralizer has symptom, geen emissie. It doesn't produce emission. So for example, but why it doesn't produce emission? So maybe there's a problem with blisters. Yeah, blisters in the neutralizers, in the neutralizer opening, and so on and so forth. So this is the knowledge graph. But of course, this knowledge graph is people in the manufacturing floor. They're not data scientists. They're not AI engineer. They couldn't understand how to operate or how to read data from it. So we have to provide them with something that is easy to operate and easy to communicate. There comes the next one, which is the GraphRAG chatbot. So from that knowledge graph, so I built a chatbot using a GraphRAG architecture. So, and this is how it works. So with GraphRAG, we know that it starts with the process of indexing. So indexes maintains data in the knowledge graph, meaning that nodes are easier and faster to search. That's the indexing process. And then we retrieve the most relevant nodes for each question. So we retrieve the nodes according to the questions that are asked by the users, and then we generate answers. Okay, so for example, there are questions. I have a problem with my PLC. It doesn't work. Why is that? Okay, so from this, from these questions, there are two keywords that we are trying to search, which is problem and PLC, and it converts to a factor, which is basically numbers. And then from that, we did retrieval. We retrieve the main components of the fault, which is an PLC with this factor. And then we did with a similarity algorithm. And then also we travels to the surrounding of the nodes that we are retrieved. So it gives more context. What is the causes? What is the measures? And then that context we combine with an LLM to generate answers. So that's how it works. Okay, so this is the examples of the final prototype. So I have a problem with my PLC. It doesn't work. Why is that? So the PLC, so it first explain what is the PLC is, and then based on graphs, so we can see there's a bracket graphs, meaning that the answers is derived from the graph. So it increased the interpretability. And then what are the possible reasons? You can see that it's shown, and then also there's a features for displaying the entities, and also the cipher query. So users can really deep dive into the cipher query and then the each particular graph in the Neo4j. Okay, so final step. Okay, 2 minutes, user evaluations. So I evaluate this with 6 evaluators for both functional and non-functional requirements, and then also feedbacks using guided surveys and also interviews. Okay, what are the result of the evaluations? So in general, when it comes to functional requirements, across all 6 evaluators from various roles, it produced quite really good scores, around 2.5 to 3. So meaning that the users, the prototype of chatbot satisfy the functional requirements. So the system produced relevant knowledge graph shown in response, and it's also easy to ask follow-up questions. So that's one of the requirements in the functional requirement. Okay, and then when it comes to non-functional requirements, I assess with four metrics: accuracy, traceability, consistency, and also trustworthiness. And as you can see, across all rows that are evaluating, so it's also produced quite good score in all four benchmark, meaning that the answer is accurate, the answer is traceable, the answer is consistent when it asks in a two different ways, but actually the same questions, and also quite trustworthy. Okay, the conclusion. So yeah, LLM extract achieve high accuracy, almost 70%, and data quality is really crucial for KG accuracy. So because there, how those the remaining 30% comes from, because it requires clarity, completeness, and also structure. And final conclusion is the GraphRAG chatbot meets users' needs when it comes to functional and also non-functional. So it effectively retrieve relevant knowledge, conversation, and also transparency in the fault diagnosis. So yeah, thank you so much for participation. So I'm open for questions. Okay, so there are questions from, so I read from the last questions, perhaps. Okay, there's a question from how the evaluations were done. Okay, so so there are two evaluations. First is evaluation for the extracted knowledge graph that was done quantitatively using four benchmark, exact matches, mismatch, missings, and also potential hallucinations that were done quantitatively, and then the pipeline or the architecture produced quite a good results, which is almost 70% of accuracy. But then when it comes to the final prototype, which is the GraphRAG chatbot, that were done qualitatively with users. So there are 6 users from various roles. Some of them are more into the machine, some of them more into the ICT background, and some of them are more into the leadership background. So we did a focus group, and then there are some questions that we defined before, and then we asked every evaluators, those 6 evaluators were typing in their systems those questions, and then we evaluate the results. And then there are some questionnaires when it comes to functional and also non-functional requirements. I hope that answers. Okay, so this answers very specific queries, which from Fedan Parek, which are diagnostic in nature. Do you think your ontology choice define the queries that can be answered? What other ontology choices can you refer to while answering other kinds of questions for large enterprise? Anything you notice while doing your experiment? You must have analyzed different queries as well. So this answers very specific queries which are diagnostic in nature. Do you think your ontology choices define the queries so that can be answered? What other ontology choices can you refer to while answering other kinds of questions for large enterprise? Anything you noticed while doing the experiments also? Okay, so yeah, as you can see, the ontology that I proposed for this research project was quite simple. It's only consists of fault location, the symptoms, the causes, and also the solutions for that particular symptoms. But in reality, it should be more than that, as we know that even the machine itself, it consists of quite complex subsystems. So there are systems for cooling, there are systems for the electronic stuff, and so on and so forth. That should be also appears in the ontology, but I didn't do that because of time constraints. But that would be that for sure would be the future directions of the research. So not only building the ontology for the fault itself, but also for the machine itself, because every machine has different characters. Every machine may be complex and consists of many subsystems. Okay, Purbasha code to check the similarities can be embedding a best approach. Okay, so for I'm not sure if I get the questions, but for this checking similarities between entities for the extracted entities, so I use Levenstein algorithm. So basically, to measure the distance between the two entities, and it's from scale 1 to 0 to 1. When it's close to 1, then it is similar, and when it's close to 0, it's highly not similar. So that's how we use. But of course, I mentioned before, it's quite manual. So after it derives the Levenstein score, so we have to judge whether these entities are really similar or not. Okay, Chen Jinjin, how long did you spend on these projects? So in total, it was 9 months. So 3 months for systematic literature review, and then 3 months for systematic literature review, and 6 months for developing both artifacts, which is the knowledge graph and also the GraphRAG chatbots. Harshit Yosi, thanks for such great session. Would like to connect to and discuss over LinkedIn. Okay, I'm very happy with that, Harshit. Just connect me on LinkedIn. Fedang Parek, like a machine card, which has its details and related profile, makes sense. Thanks a lot for this super stuff. Subham Sartful, thank you for the session. Yeah. Okay. So thank you guys. So I hope I answered everyone's questions. So if I miss it, so I'm really sorry. But of course, you can drop me a comments or add me on LinkedIn. I would really help. I would be really happy to discuss more with you guys. Thank you.